So in the previous class, we talked about the multi-arm bandits problem. I was confused when you guys were in the seminar. Rank and selection, right? It's very similar to multi-arm bandit. And the multi-arm bandit, you have multiple alternatives. You just try to select the best one, right? And on rank and selection is also you have many alternatives. You're trying to select the best one. Okay? And they will consider the mean as a target. You want to try and select the one with mu k, the biggest mean or the minimal mean, right? Here we're trying to choose the one with bigger mean and good distribution, so that every time you pull the arm, you get money back, right? So I think people has different ways to do the research or to solve a problem, and you may find the commonality between those approaches to tackle a particular problem, and also note what is the difference. Okay. Yeah. So now let's get back to the Markov decision process. So outline of today's lecture is first the agent-environment interface. Then we have second one is the agent's action and the reward. And then we're going to give the formal definition of Markov decision process, and also what is the value function and what is the optimal value functions. In the end, we are going to discuss the Bellman equations and give an example. So the first one, agent-environment interface. So you have an agent. This agent is going to select action. This action is going to be you act on the environment, okay? And then the environment, based on the action, the environment is going to respond and give you a reward and give you a new state. And then based on in time t, you have a state and a reward, and then you give to the agent.
Can you turn off the lights? Or would that be more clear?
Turn off the light? Turn off the light? You guys are going to be sleepy, I guess. Is this better? Make me feel like I'm in the spotlight. Yeah.
Actually, I wanted to reduce the lighting. My eye has a condition. Yeah, this is perfect.
I just think this is too dark. Okay, maybe like this. Okay, better?
It's better for me, I don't know.
Okay. Yeah. Okay. Good. So first, if you are an agent, you're trying to see what the state of the system is, right? And then based on the reward that you have got, and then you're going to choose an action. The action is going to, once you choose an action, the environment is going to give you a new state and then a new reward. So this is like you have a state, then you choose an action, and the action is going to give you a reward, and then you get into a new state. And then the new state, you evaluate this state, you choose another action. The action will give you a reward, and then you get into another state. Okay? It's like chain effect. The agent and the environment interact at discrete time steps. So here in Markov decision process, right now we're talking about discrete time Markov chain. At each time step, the agent receives some representation of the environment state. At each time step, the agent receives some representation. You see here, in Markov chain, so far when we talk about Markov chain, most of the states are clearly defined. Okay, and you were given what is a state. And even in the homework problems, it's easy to see, right, how many people in the counter. But in some real world problems, it's very hard to define the state. Sometimes you got a signal, okay? Sometimes you got an image. You need to extract the state from the image or from the signal. So this is what they meant. They mean, or what it does mean, some representation of the environment. That means you need to analyze the feedback you got from the environment. And then you do some extractions. And then you should have a good extraction of the state. Otherwise, if your state is not well defined, then the whole formulation will not be well established. And on that basis, you select an action. Once you have the state, clearly defined state, and then on that basis, you select an action. As a consequence of its action, the agent receives a numerical reward, RT plus 1, and finds itself in a new state. So this is just keep going iteratively, and or you can call it sequentially over time. Okay. So this is an agent involvement interface. Okay. Now, the next one is what is the policy? Okay. What is a policy? Policy is a mapping from states to probabilities of selecting each possible actions. Policy means you give me a state. I tell you what action to choose. This is policy, right? You give me a state, and I say you should choose this action 1 or action 2. But instead of directly deterministic policy, this is a probability to choose a particular action. So that's why we call it a policy. Otherwise, it's not a policy. It's like a checkup table, a lookout table. Right? You have this, and you in this in this. But it's not a lookout table. There's still randomness. You have a probability. It's just that you have a higher probability to choose this and a lower probability to choose another actions. So a mapping from states to probability of selecting a possible action. This is pi t. And you see condition on the state, and then we choose an action. And if we define this pi, and then this will be the probability that we choose this particular action if state equals to Ts. So again, policy clear, right? Policy based on the state, and what is the probability to choose an action. This is your policy. Okay? Because later we're going to have many definitions. So the first definition is a policy. What we want to achieve in decision making is an optimal policy. Okay? You want to find an optimal policy that's given a state, optimally you choose an action. Everybody agree, right? So the agent's goal is to maximize the total amount of reward it receives. So the rewards specify what the agent needs to achieve, not how to achieve it. Okay? So the simplest and cheapest form of supervision. You see, in multi-arm bandit problem, you only have one state. Okay? You don't have many states. You don't have you are in one state and then you get into another state. You only have one state and then you have 4 arms or multi-arms, K arms. You want to choose which arm which arms to choose. Okay, you only have one state and a couple of actions. But here we are extending this multi-arm bandits into a Markov scenario. That means you are in one state, you have a set of action. Now you are evolving into another state, you have another possible set of action. Your action set may also be different. Make sense? So multi-arm bandit is actually the first form of the MDP. We need to master multi-arm bandits before we move into this one. Okay, so that's why I talked about multi-arm bandits in the previous class, and then getting to the Markov decision process. Okay, Markov decision process. You see here we have studied the discrete time Markov chain, continuous time Markov chain, but this one is not. It is not called DTMC. It is called Markov process, but we add a term here called decision. Markov decision. What is new here? What is new here is in the next slide, I guess. Okay, not in this one. This is Markov process. Markov process formally describes an environment. Okay, the environment is fully observable, and you know the transitions. And the current state completely characterizes the process. That means if you know the current state, you know the probability of transition into different state. And Markov property is if a state ST is a Markov if and only if, you see, current state, only the current state ST characterize the process. All the history can be dropped. So only based on the current. So this probability, given st, and you have probability st plus 1 is actually equals to st plus 1 given all the history. Okay? So the future is independent of the past given the present. The state captures, okay? The state captures all relevant information from the history. So once the state is known, the history may be thrown away. Okay? The state is a sufficient statistic of the future. So this is a Markov, what we have discussed. So the transition matrix for Markov, we define this transition matrix. If you are in this S, what's the probability you are in the S prime? S prime is the next at t plus 1. So for Markov state S and a successor state S prime, the state transition probability is defined as PSS prime. You see here, this is Pij. What do we define Pij? Okay, when you are in state I, what is probability into state J next time point? So state transition matrix P defines transition probability from S to all successor state S prime, okay, where each row of the matrix sum to 1. It's clear, right? P11, Pij, P, capital P matrix. Okay, so this is a state transition matrix. Okay, now it comes to the difference. We adding a new component into Markov process. So previously we only have state and transition probability. Okay, only a state and transition probability. Once we know this two, we know the long-term fraction of time you're going to stay in a particular state. And that one we have pi. But here we also have pi. This pi will be policy. Okay, in this literature, MDP literature. But that pi is a steady state probability. Make sense? Am I making sense? The pi. This pi, we have pi here. Pi is the policy. But previously in DTMC or CTMC, we also have pi. That pi is the steady state probability. It's different. I hope everybody captures this difference. But Markov decision process, you see, we are moving from this state and transition probability. You see, this state and transition probability, you still have transition probability. But you still have state. But we added the action. Because when you are in a state, you choose an action. Then you evolve into another set of state, right? But if you don't choose this action, you choose another action at this state, you will evolve into another set of state. Make sense? You have probability to enter another set of state. So this is state and then action. We have action and then we do the transition. Based on the action, you do the transition. And then this transition probability matrix not only depending on the state, also depending on what action you choose. Then once you choose an action, you will have a reward. And also you have gamma. What is gamma? Gamma is a discount factor. That means we have long-term reward. Okay, so S is a finite set of states. A is a finite set of actions. So P is a state transition probability matrix. You see here, we add A. Previously, when we talk about DTMC or any jump matrix in continuous time Markov chain, right? We only have transition probability matrix. We don't have any action. And then here we add action. If you have action, then you need to choose the proper action, okay? Optimal action. So now the new transition probability matrix, depending on what state we are in right now, and also what action we are going to choose. And then what will be the new state. Make sense? And then given the current state and given the action, you are going to evolve, you have probability to evolve a new state. And the probability depends on the state you are and also action you choose. So reward is R is a reward function. This reward actually depending on which state you are in and which state you're going to get into and also which action you choose. So given the state, and you choose a proper action, and then you evolve into a different state, and then you have reward. That means if you are in a state and then you choose an action, you are going to have a reward based on your action. Mm-hmm. And gamma is a discount factor. Discount factor, you prefer present. If I am going to give you $100, of course you're going to prefer you have it right now. Or I can give it like 10 years later. And then you say, oh, I want it right now. That means the present value and the future value of money is different. And the present reward and the future reward is different. Okay? So reward, the return GT is the, you see GT is the, this GT reward, this reward is what you get in a particular time. Okay? T plus 1. But GT is different. GT is the total discounted reward from time step t. That means from time step t, and then you're going to evolve, right, over time until the end. So you are going to go to t is the present time, and then you choose an action, you get a reward. And then you are going to do the transition, and then you choose another action, you get a reward. GT is the total discounted reward. Okay? And GT is different from R. And so that's why we're going from k equals to 0 to infinity, gamma k RT plus k plus 1. So the objective is to maximize long-term future reward. Long-term future reward. That is to choose an action so as to maximize not only RT plus 1. You need to consider RT plus 1, RT plus 2, RT plus 3 as well. So the discount factor is the present value of the future rewards. And of course, it's between 0 and 1. And this values immediate reward above any delayed reward. Okay? If you give it a 0, you see if you give 0, then GT equals to RT plus 1. That means this is called myopic. Myopic, you only look at the present. Okay? If you give it a 1, if you give it 1, they are all equally weighted. You see, this is a 1, this is 1. Everything in the future is equally weighted. But of course, you want to value the current money a little bit more, right? So that's why you give it maybe 0.9, and then this is 0.9. Next one will be 0.9 power 2. And then 0.9 power 3. That means future value has decreasing weight. So 1 is very far-sighted, and 0 is very myopic. So this is what we call myopic and far-sighted evaluation. So why discount? Okay, most Markov reward and decision process are discounted. Why? Because this is mathematically convenient to discount rewards, avoids infinite returns in cyclic Markov process, and also uncertainty about the future may not be fully represented. If the reward is financial, the immediate reward may earn more interest than delayed reward. Okay? Animal or human behavior show preference for immediate reward. It's like that, right? It's sometimes possible to use undiscounted Markov reward process, that's gamma equals to 1, if all sequence terminate. Okay? For example, in the additive manufacturing, the sequence will terminate. You have how many layers? At most, like 1,000 layers, at most of them. But if you have a really big, then you have more than that. But this is finite. You cannot print something 3D printing. You cannot have infinite layers, right? So all of them, they terminate. So you can use 1 because it's a limited number, finite number of layers. A policy is a distribution. You see, previously we talked about the probability, selecting an action based on the state. So now we're talking about distribution. Distribution is a probability. This is a S, and then based on your S, you have A1, A2, A3, right? They have different probability to be chosen. That is, given the state, what's the probability to choose a particular action? This is a distribution. So you see, policy is a distribution. Make sense? Policy is not a lookup table, like you choose this and choose this, right? It's a probability. And if you are in this state, how do you select a particular action? It's like Randall. You remember the Randall we have? Okay. And then you can have a uniform random number generator. And then because if you are in this state, you choose all possible actions, the probability sum them together should be 1, right? Then you generate a uniform number between 0 and 1. You see where it falls into. Then you choose the particular action. If the action probability is higher, then you have a higher probability to choose that. Okay? So a policy fully defines the behavior of an agent. MDP policies depend on the current state, not the history. So policies are stationary, time independent. Okay? Oh yeah. But some of you come to my office talk about the time dependent policy. Actually, what you are going to make, the decision you're going to make actually depending on the time. Okay. But you may reformulate the problem. If you have a time-dependent, independent one, it's much easier to solve. It's actually depending on how you formulate the problem. Okay? And then you can make it time-dependent or make it time-independent. Make sense? Okay. Okay. Now, policy are stationary. So if you have a non-stationary policy, you're trying to complicate things. Okay? Make sense? So solving Markov decision process, finding the optimal policy. So we have 2 ways to do it. There are 2 objectives. The first one is called prediction. Okay. You are not allowed to find out the policy, but I give you a policy. And then estimate the value function of states and state action pairs. Okay. This means that if I give you a policy, just tell me how good the policy is. A fixed policy. Fixed policy can be a random policy. Random policy means if I'm standing here, okay, if a robot, okay, has the opportunity to go 2-dimensional space, okay, go to the north, south, east, and the west, the probability to go each direction is equal. Now tell me how good the policy is. And this is called policy evaluation. And then you want to predict how good the policy is. And the second one, based on your prediction, now I change the policy a little bit. Tell me whether you have a better policy. So this is called control then. If you only predict, you were given a policy, you predict how good it is. This is prediction. And then now let me change it to another policy. Is it better? So this is called control. Estimate the value for the optimal policy. That means you keep trying different policy. But there is a searching strategy. You search for the optimal policy. Always you want to choose the action that maximizes your reward. So that's, if you add a max, then you go to the control problems. So that's why prediction, depending on the pi. You were given the pi, you estimate V or Q. V is the state value function. Q is the state action value function. That means you define the state and action, then what is the value? And the star means you're going to take the max, either maximization or minimization, depending on how you define your reward. So once you have star, that means this is control problem. So you have prediction problem and a control problem. Value functions. Value function measure the goodness of a particular state or state action pair. Okay? How good is for the agent to be in a particular state or execute a particular action at a particular state. Of course, that depends on the policy. Okay? This, of course, depends on the policy. Optimal value function measure the best possible goodness of the state or state action pairs under any policy. Now let's look at the value function, state value function. You see state value function, this is defined as state value function. This is action value function. So this one is V. V is the state value function, depending on pi and how good your state is. Of MDP is the expected return starting from state S and the following, and follow the policy. If you follow the policy, if you're in state right now, if you follow the policy, you just keep evolving and then see what is the value of this state. Then if you can give me the value of a state, then if you evolve into a particular state, immediately you know how good this state is. Okay? So this is ST equals to S, and what is GT? You know, GT is total discounted sum reward. That means you have RT plus 1, gamma RT plus 2, gamma RT plus 3, and gamma square RT plus 3, and then you keep evolving. So this is why this is expected return. You start from state, and then following the policy, you see all the different states. And then every time you got a reward, you add them together. Then this note here, this is an expectation. Okay? Because over here, this is expectation over the pi. This is also expectation. You are looking at the expected reward because this is a random process. You have a distribution, not deterministic. Like if you give me a state, immediately I have fixed like reward or something. You have a random policy, and you can get into different action. Different action can also give you different reward. But you are interested at the expected, so that's why the expected return, the average return. The action value function, actually you want to state and also the action. You want to evaluate how good this pair is. That means you are in state, and now you can choose 4 actions, right? Tell me how this state paired with this action, this state paired with this action. Which one is better? Which one give me more returns? Not just the immediate return, but GT. Expected return, starting from state S, taking action A, and then following the policy. Following the policy means you're giving me the policy, and I keep evolving. So you give me the state, give me the action, and then I just follow your policy and then keep evolving. Why we have expectation over the policy? Because policy is a random distribution. Policy is not fixed. Policy is a random distribution. If you are in a particular state, what's the probability to choose an action? That's why we have expectation. Okay? So this is Q pi SA. You see, Q depends on the pi, depending on what state you have, what action you take. And V depending on the pi and also only the state. The optimal value state value function of MDP is a maximum value function over all policies. Okay? The maximum value function over all policies. Make sense? So the optimal state value function is a maximum value function over all policies. That means you have all different kind of policy. Now you give me the best one. You have policy 1, policy 2, policy 3. Now in a particular state, you must have a very good policy that give me the overall the maximum return. So this is called V star. And this we are evolving into a control problem. The previous one is only prediction. You give me a particular policy, how good is the state value function or state action pair value function. So optimal Q star SA also you have pi and different kind of pi, and you want to choose the best one. The maximal action value function over all policies. So that's why we have V star and Q star.